Now periodicity. Along the period, what happens? Along the period, if you take second period elements, in second period, elements are enter into second energy level. In any period, suppose if it is at second period, electrons will enter into second period, second energy level. In third period, third energy level. Fourth period, fourth energy level. Fifth period, fifth energy level. Sixth period, sixth, like that. So now we are considering second period elements. In second period, we have lithium, which is valence electron is 2s1. Then beryllium, which valency is 2s2. Then boron, 2s2, 2p1. Carbon, 2s2, 2p2. Then nitrogen, 2s2, 2p3. Then oxygen, 2s2, 2p4. Then fluorine, 2s2, 2p5. Then neon, 2s2, 2p6. So in any atom, as we take in a period, the last electron will enter in second energy level only. Last electron will enter in second energy level only. Now here what happens? This is nucleus, first energy level, and this is second energy level. That means the distance between these two is same. Here we have lithium and here we have neon. In lithium, 3 positive charges are there and 3 negative charges are there. Whereas in sodium atom, we have 10 positive charges and 10 negative charges. So in between that, remaining elements are in between them. So in lithium, 3 positive charges are attracting 3 negative charges. In beryllium, 4 positive charges are attracting 4 negative charges. In boron, 5 positive charges are attracting 5 negative charges. In carbon, 6 positive charges are attracting 6 negative charges. In nitrogen, 7 positive charges are attracting 7 negative charges. In oxygen, 8, fluorine, 9, so on. But the distance between the nucleus and lost electron is same, because all are in second energy level. From lithium to neon, the distance between the nucleus and lost energy level is same. There is no change at all. But the magnitude of positive and negative charges are increasing. Without any change in its distance, if magnitude of charges are increasing, the electrons will closerly attracted by each other. That means electrons will have more nuclear attraction as nuclear charge is increasing. Due to that, as atomic number is increasing and the electrons are entering into the same energy level, these electron cloud will move towards nucleus and the radius of an atom will gradually decreases. Electrons are moved towards nucleus due to the increase of nuclear charge without increase in its radius. That's why from left to right in a period, as atomic number is increasing, atomic size is gradually decreases. This is observed in second and third period elements. In second and third period elements, as atomic number is increasing, atomic size is gradually decreases like this. This is the trend in second and third period. Now let us observe the condition in fourth period. This is gradual decrease of atomic size. in second and third period. This is in second and third period. Now what happens in the fourth period? Let us observe in fourth period. Fourth period, first element is potassium and electron is in 4s1. And the next element is calcium, its electron is in 4s2. Then scandium, first electrons are in 4s2, then the electron is in 3d1. Gradually from scandium, titanium, vanadium, chromium, manganese, copper, manganese, ferrous, cobalt, nickel, copper and zinc. Here in 10 elements, the electron will enter into 3d1 to 3d10. 3d1 to 3d10. Then after that, gallium, germanium, selenium, the electrons are again in 3p level. 3p1, 3p2, then arsenic 3p3, next selenium 3p4, like that. So now here in the transitional elements, that is from scandium to zinc, the electrons are entering inner shell. In potassium and calcium, electrons are in the valency shell. From scandium onwards, the electrons are entering into the inner shells. So those electrons which are entering into the inner shells will act as screens, because when atomic number is increasing, nuclear attraction is increasing. But here these electrons which are present in between, this is the valency shell. Here we have 2 electrons in the valency shell, but new electrons are entering to the inner shells. In second and third periods, last electron will enter into the last energy level. But in the transitional elements, last electron is entering into the inner shell. When they are entering into the inner shell, distance between the nucleus and electrons is not changing. Due to the increasing of atomic number, nuclear charge is increasing. When nuclear charge increases, automatically nuclear attraction increases. When nuclear attraction increases, that attraction should have effect on the valency electrons, because the position of valency electron will decide the atomic size. Now, though the nuclear charge is increasing, though the nuclear attraction is increasing, this effect was not focused on the valency electrons, because here new electrons are entering into the inner shells, which protects the nuclear shell, a nuclear attraction over the valency electron. These electrons which are present in the inner shells will shield the nuclear attraction. So though nuclear charge is increasing, because of the shielding effect, this effect is said to be shielding effect, because of the screening effect or shielding effect of these electrons which entering into the inner shells, will not affect the valency electrons. That means the increasing of nuclear charge has no effect on the valency electrons. That's why the decrease of atomic size, as we observed in second and third periods, is not significant in the D block elements of fourth and fifth periods. That's why you will observe a decrease in 2 elements, that is in potassium and calcium, you can observe the decrease of atomic size. But after that, from scandium to zinc, there will be no decrease at all, up to zinc. Then you will find the decrease. That's why the transitional elements, that is D block elements, are almost in same size from scandium to zinc, all the 10 elements will have almost same in size because of this shielding effect. Now once again I will explain to you the shielding effect or screening effect. Here we have a nucleus, here we have a valency electron. Generally, when new electron is entering, it should enter into the valency shell only. But in transitional elements, instead of valency shell, the electrons are entering into the inner shells. So when electrons are entering into the inner shells, these electrons will act as screens and protect the nuclear attraction, so that this nuclear attraction due to the increasing of atomic size have no effect on the electron which is present in the valency shell. So though the nuclear charge is increasing, since this effect is not found in a valence electron, the regular decrease of atomic size due to the increasing of nuclear charge is not observed in d block elements or transitional elements. That's why the size of transitional elements present in a period is almost similar. That's the reason why they are able to form alloys very easily than the other elements. Crystal structures are easy to form alloys, the alloys. Now let us observe this effect in sixth period elements. So in the case of sixth period, it is different, because in sixth period the first element is cesium. After cesium we have barium. After barium we have lanthanum. Lanthanum onwards in the next 14 elements. The last electron will enter in n-2 f orbital. That means here in the d block elements, this is the fourth energy level, and this is the fifth energy level, and this is the sixth energy level. Now here the valence electrons are in sixth period, 6s1 and 6s2. So after lanthanum, cerium to lutetium, the electrons are entering into the inner shells just like in transitional elements. But here these electrons are entering into the f orbital. Because of the peculiar shape of f orbitals, the screening effect which we expect, just like in the transitional elements, is not observed in lanthanides. Because of its peculiar shape, the electrons which are into the inner f shell cannot exhibit that shielding effect. Because of the lack of that shielding effect, as atomic number increases, nuclear charge is increasing and nuclear attraction is increasing. As nuclear attraction increases, the valency electrons will move closer to the nucleus. That's why we can observe the regular decrease of atomic size in f block elements, where we have not observed the same in d block elements. Because of this, a regular decrease of atomic size is observed in lanthanides, which we call it as a lanthanoid contraction. Because of this lanthanoid contraction, the d block elements present in the sixth period, that is 5d series elements, will have almost equal size of 4d series elements. Generally, 5d series elements should have more atomic size than 4d. But 5d elements, because of this lanthanoid contraction, their atomic size is almost equal to the size of 4d. This we call it as a lanthanoid contraction. What is lanthanoid contraction? In lanthanoid elements, that is from cerium to lutetium. The differentiating electron will enter into n minus 2f orbital. In these elements, valence electrons are present in 6s2, and the differentiating electron is entering into the 4f, n minus 2f. That is, electrons are entering into the inner shells. On traditional way, if you think that these elements should show screening effect, but because of the peculiar shape of f orbital, the electrons which are entering into the inner f shells will not have that shielding effect. When shielding effect is not there, nuclear attraction over the valence electrons is increasing as atomic number increases. That's why in lanthanoid elements, as atomic number increases, atomic size decreases gradually. Not only in the lanthanoid elements, in their +3 ions also, the regular decrease is observed. So the regular decrease of atomic size in lanthanoids or ionic size in +3 ions is called as lanthanoid contraction. Because of this lanthanoid contraction, the next elements after lanthanoids, that is 5d series elements from hafnium to radon, their atomic size also less than the expected size. That's why, though they are present in the 6th period, we call them as a 5d series elements. We expect their size is more than 4d series elements, that is the d block elements of 5th period. But because of this lanthanoid contraction, these 5d series elements will have same atomic size as 4d series elements. So that's why in lanthanoids, this position of this atomic size is further like this. That means the further decrease is observed, and then it will be like this. This is in the 6th period. So you will find a flat in 4th and 5th periods, whereas in 6th period a regular decrease is observed because of the lanthanoid contraction. So atomic size of an element is gradually decreases from left to right in a period. But in a group, what happens? In any group, if you take, what happens? In a group, if you take, let us take first group elements. Lithium is in 2s1, sodium 3s1, potassium 4s1, cesium, rubidium 5s1, cesium 6s1, francium 7s1. So if you move from top to bottom in any period, not only in the first period, if we move from top to bottom, the differentiating electron will enter into the next higher energy level. So automatically the radius of an atom is gradually increases, so that atomic size will increases. In any group from top to bottom, as you move, the atomic size is gradually increases. In a period, it gradually decreases, with some exceptions in transitional elements. Whereas in group from top to bottom, atomic size is gradually increases. This is about atomic size and its periodicity.